So let's talk about polar compounds and non-polar compounds. So in chemistry, we want to understand what compounds are polar and what compounds are non-polar. So polar things dissolve in polar environments and non-polar things dissolve in non-polar environments. So we want to classify things as either non-polar or polar. It's very hard to classify most things as polar or non-polar, but there are some examples where they definitely are polar and definitely are not non-polar. So when you do your examples, they're most likely going to be one of the extreme. When you start coming into that borderline between polar and non-polar, it gets a little bit more grey, and it's the degree of polarity that you have in that particular compound. So when we're looking at our small molecules that we're assigning our simple shapes or molecular geometries to, we can classify those as polar and non-polar. When we're getting into larger molecules, organic compounds, again, they're fairly easy most of the time to classify them as polar or non-polar. So the things we're looking for is if you have electronegative atoms that are cancelling out electronegative atoms. So for example, if you have water and we have two lone pairs and two bonding atoms to it, which are our hydrogens. And this shape here is actually a bent conformation, so it's a bent shape. So these hydrogens are slightly delta positive, if you look up the electronegativity value, and this one's delta negative. But because these delta positives are not directly opposite each other, they don't cancel out. So we have an overall vector that goes through the molecule and towards the negative. So this is the positive region, this is the negative region, and this is a polar molecule. Now, if we have something that cancels out, like Cl4, this would be a tetrahedral shape. So each of those chlorines will have an angle of 109.5 degrees, and they will pull each other at exactly the same strength because all these delta negative chlorides would have the same electronegativity. So overall, they would cancel out, and this would be nonpolar. So you can see when we're looking at these, we need to think about what the shape is. Are they cancelling each other out? If they are, they're non-polar. If they're not, they become polar. So if something has a charge on it, okay, it's automatically can be considered polar. And that is because polar compounds generally dissolve in water, which is our classic kind of polar example, and ionic compounds will dissolve in water. So you could call them polar. Our classic non-polar ones are alkanes, so carbon compounds that are saturated with hydrogens, so they have the highest possible number of hydrogens attached. And the electronegativity difference in this is so marginal that everything cancels out and is also considered to be non-polar. So when we're looking at organic chemistry, we want to think about the ratio of those electronegative atoms to the electropositive atoms. So if we look at methanol, and butanol, we can see that our electronegative atom is oxygen, and all the rest are not electronegative. So the number of electronegative atoms is 1 to, let's just count our carbons. So we've got a 1-to-1 ratio of electronegative to electropositive. So this is very polar, if you want to think of it like that. It's just one way of conceptualizing it. So 1-to-1, so it's quite polar. Here we've got 1, and we've got 1, 2, 3, 4 carbons. So it's a 1-to-4. So it's less polar. It's still got this OH, which is able to hydrogen bond donate and accept, so it's still quite polar, But this is less polar than this example here. Okay, so the polarity, I'll do another video on polarity, but this is just to get you thinking. So think about the molecular geometry, think about those ratios, and then I'll do a video later about the functional groups and how they affect the polarity. Thank you.